Welcome, everybody. Good evening. My name is Father Matthew Doherty, and I serve the college as an assistant professor of biology, as well as special assistant to the president for mission integration here at St. Norbert College. It's my great pleasure to be with you tonight, serving as a guide for this event this evening. My first task is to invite our president forward, Dr. Lori M. Joyner, who is the 9th president of St. Norbert College, to welcome you to this special evening. Dr. Joyner.
Good evening and welcome to our academic home. Tonight's gathering highlights the gift of the Catholic intellectual tradition, recognizing the dynamic partnership between faith and reason. The three core traditions at St. Norbert College are Catholic, Norbertine, and liberal arts. These rich traditions provide fertile ground for us to explore the big questions, such as what does it mean to be human? Where do we come from? How do we build a meaningful life? And what are our responsibilities to each other? We have been blessed with our share of Norbertine scientists on the faculty here at the college. I hope you had a moment to appreciate the exquisite banners out in the lobby created by Dr. Michael Holstead, raise your hand, director of our Center for Norbertine Studies. The display shines a spotlight on how the order has advanced scientific curiosity and wonder for much of its 900-year history. As part of the college's Support What Matters campaign, Dr. Benjamin Chu, a 1955 graduate and past trustee of St. Norbert College, made an extraordinarily generous donation to support this new annual lecture series exploring the intersections of science, theology, the beauty of creation, and transcendence. We are fortunate to initiate this series with tonight's esteemed lecturer, Brother Guy Consolmagno. On behalf of our community, I thank you so much for joining us. And now I invite my colleague, Father Matt, forward to introduce Brother Guy. Thank you.
Thank you, Lori. I have the distinct honor of introducing Brother Guy Consolmagno of the Jesuit Order. Brother Guy is a Jesuit and is the director of the Vatican Observatory in Rome. He's a native of Detroit, Michigan, where he earned his undergraduate and master's degrees from MIT and a PhD in planetary science from the University of Arizona. He was a postdoctoral research fellow at Harvard and MIT. He served in the U.S. Peace Corps in Kenya and taught university physics at Lafayette College before entering the Jesuits in 1989. At the Vatican Observatory since 1993, in 2015, the Holy Father, Pope Francis, appointed Dr. Consolmagno director of the Vatican Observatory. Brother Guy's research explores connections between meteorites, asteroids, and the evolution of small solar system bodies. He has observed the Kuiper Belt objects with the Vatican's 1.8-meter telescope in Arizona and measured meteorite physical properties to understand asteroid origins and structure. Along with more than 250 scientific publications, he is the author of a number of popular books, including Turn Left at Orion, Would You Baptize an Extraterrestrial? Interesting. And When Science Goes Wrong. In the year 2000, the International Astronomical Union named asteroid 4597 Consolmagno in recognition of his work. In 2014, he received the Carl Sagan Medal from the American Astronomical Society Division for Planetary Sciences for excellence in public communication and planetary sciences. He currently serves as chair of the IAU Mars Nomenclature Task Group and vice president of the Meteorological Society. I should also say, Brother Guy told me that this International Astronomical Union is the one that's responsible for killing Pluto. So he's the guy. All the stuff you learned as a student in elementary school is now wrong because of Brother Guy. So with all that, let us warmly welcome Brother Guy Consolmagno.
Thank you. And that's actually quite apt, because what I'm talking about today are the things that we learned in grade school that turn out to be wrong, and why we trust science nonetheless, even though it goes wrong on occasion. It's, as you know, based on a book. I'm only the co-author. My co-author, Chris Graney, is the historian of science. He did all the research. I came up with all the jokes. The idea behind the book really got started with the COVID pandemic and the somewhat sad misunderstanding of what science can and cannot do. It really came home to me when there was a friend of mine who lives up in the UP. I remember we met years ago. She had a 14-year-old kid fascinated by science, wrote a paper for her 8th grade about the science of the Vatican, and the teacher said, "This is a failure, you just made that up. The Vatican doesn't do science." I had to write a letter on Vatican letterhead saying, "Yes, we do." Well, she grew up, married a wonderful guy, has 2 kids, remind me of what she was like when she was that age. And her husband was a vaccine denier and died of COVID. And it was partly that coming, you see the statistics, but when it's somebody you know, you wonder, he was a good guy. He was a smart guy. How does it happen that people put too much faith or not enough faith in science? And what does it say about how we put faith, for that matter, in faith? That said, before I jump into the rest of the talk, I want to start with a little 5-minute movie to give you a sense of what the Vatican Observatory is about, because I know a lot of people are puzzled about that. So the guy giving the talk at the beginning is kind of a goof, but I hope you can look past that. Both science and religion are conversations about the universe. They're ways of learning how we interact with this universe. It's not simply a question of, is there a God, but there is a God, now what do we do? It's not just a question of, there are a bunch of stars, but rather, why are there stars? How do they work? How does that tell us how things work here on Earth? The interaction that I see in my own life is that religion gives me the reason to do the science.
Back in the papacy before Francis was Benedict, and one of his lines in a final elocution to the fathers of the General Congregation was, "Go to the frontiers." Well, there isn't much more frontier than 3.7 billion years away.
The first official interest of the Church for astronomy started in 1582 with the reform of the calendar. Then in 1891, Pope Leo XIII wanted to have an observatory to show that the Church is not against science, but the Church promotes good science.
They start out by having telescopes on the Tower of the Winds, and then on the walls surrounding the Vatican, as the city lights grow, and as the Italian government gives them back the territory out in Castel Gandolfo. In the 30s, they build new telescopes on the roof of the Papal Palace in Castel Gandolfo, best telescopes of their era in the 1930s. By the 1980s, light pollution makes those telescopes unusable, so we build a new telescope in the dark skies of Arizona.
I'm Father Jean-Baptiste Kikwaya Eluo. I'm working in 3 projects. The first one is NEOS, Near Earth Object. So what I'm doing with NEOS is just observe them using our modern telescope VAT. The second project is meteors. I worked on very faint meteors, what we call shooting stars. And the third project is set fireball network. They will have 4 cameras here around Tucson, so that actually we can monitor any fireball getting into the Earth atmosphere, the region.
This telescope, the Vatican Advanced Technology Telescope, it was the first of the new technology telescopes that has been considered pretty much the norm now in developing telescopes. With the advance of computer technology, we have the capability of bringing that advanced technology directly into our telescope. So it's an expandable, it's almost like it's a living machine, so it can grow as technology grows.
It is still very important to maintain scientific research at the Vatican, simply because there is still a lot of confusion about this relationship between science and faith. We are not out here trying to prove the existence of God by looking through a telescope. That's not what we're doing. But we can say that if we want to obtain any reasonable results looking through that telescope, we need to do it embracing a certain work ethics that is, in fact, the same work ethics that the Bible itself tells us through commandments and through the Gospels to embrace.
Human beings look at the stars and wonder. They want to know, what is that? What is that about? How do I fit in? They hear about the moon landing and they want to know, what was that like? If we're part of the human race, we're part of the race that went to the moon. We're part of the species that looked at the stars and wondered, what the heck are those things? Looking at the sky reminds you that there's more to the universe than what's for lunch. What's more, if you believe in a universe that God so loved that he sent his son, then not only are you going to want to study the universe because it's kind of cool, it's an act of worship. It's an act of getting closer to the Creator and getting closer to a universe, as St. Athanasius said 1,500 years ago, was cleansed and quickened by the Incarnation. Then, doing science is an act of worship. I just wish they had that kind of music when I was actually doing my work, you know. Really pulls it all together. What I'm going to do in this talk is give a couple of examples of cutting edge for its day science that turned out to be not only wrong, but I hope amusingly wrong. And then one example that's not so funny. All of it to make you recognize that science is in the business of getting it wrong. It seems very odd, but it's only when you learn what's wrong that you're then motivated to find out what might be right. If you think you know it all ahead of time, then science becomes dead. We'll start with one picture of the universe in our cosmology. Many of you may have seen this picture before, this medieval view of the universe. This actually is not a medieval view of the universe. It is a 19th century idea of a medieval view of the universe. It was invented in the 19th century because they wanted to believe that people in the past were stupid and that they were much smarter. Too much of our understanding of science in the past concentrates on the things they get wrong. I want to show how the things they got wrong were essential to us getting right. Scripture does start with this view of the universe, a flat world, a dome overhead, and chambers where rain and snow are above and below. We look at this and we know, oh, well, that's not what the universe looks like, but we only know that because we've been taught that or we saw pictures. If you, otherwise uneducated, went outside, that's what you'd see. There is a dome. It goes all the way to the horizon. Water does come out of the sky. And if you dig a hole, you can find water down there too. So something has separated the water above and below, and here we are. It must be that dome that we see. It's based on clear observation and at the time that Genesis was written, it was the best science of the day. The difference was the Babylonians who had come up with this picture said that dome was the carcass of a dead dragon that the gods had fought, and that human beings somehow by accident managed to become created. They snuck into that dome and built the greatest thing in the history of the human race, the city of Babylon. When Genesis was written, the Hebrew scholars, the ones who have been carted off to Babylon and heard these stories, said, okay, that's what the universe is, we all agree. But here's what's different. In the beginning, God's already there. God is not part of the universe. God is not part of nature. God is supernatural. And by supernatural, I don't just mean, Casper the Friendly Ghost. If there was such a thing, that would just be another part of nature. God is outside of nature, and because God creates from outside of nature, God can give nature meaning in a way that nature cannot give itself meaning. Wittgenstein says this. He describes how a chair has meaning only because there's somebody who's not chair using the chair. The universe has meaning only because there is a creator who's not universe, who gives it meaning. In the Babylonian myth, everything happened by accident. In the Hebrew myth, in Genesis, it is the deliberate act of God. And the first thing God does is said, let there be light, so that I'm not hiding anything. I'm creating the universe as logical as day follows night. At every step along the way, I say, this is good. Somebody has told me that you could translate that as, God looking at the world and saying, yeah, that works. Now what do I do? And most importantly, what is the climax of creation? Not the city of Babylon, not my own glory. What is the last and most important thing that God creates? The Sabbath, the day of rest, the day when we stop worrying about what's for lunch and we start asking ourselves, what is this universe? Who is responsible for it? How can we study and adore God who created it? We are made for the Sabbath. We are made to be astronomers or poets or photographers or people who do all the things that feed our souls because we don't live by bread alone. I'd read that someplace. Within 100 years of Genesis, it was obvious to people looking a little bit further that, in fact, the world was round. You can see the shadow of the round earth as the moon passes through the shadow. You can also see that when you go north or south, that different stars are visible as you move further south. You can also see that on the longest day of the year, a beam of light will go down a well, completely illuminating it in Syene because the sun's right overhead. But you go 1,000 cubits to the north in Alexandria, and it casts a shadow. And from the length of the shadow, you can calculate how big the earth is, and they got it right. What's more, by studying how the world is put together and observing what you see, you begin to see that there are different layers. There's all these things out in the sky that move in front of each other, the planets, the stars that seem to be fixed all together. And then here on the earth, there's dirt. Stuff falls to the center. That must be its natural place. Water, which, the dirt will fall through the water bubbles up. Air bubbles through the water so that it's the next layer. And then finally fire, the auroras, the sunset. You can see these different things in the sky. It is based on observation. The fact that people are observing the universe, Aristotle in particular, and generalizing from what they see into general principles is an enormous step ahead in science, even if it is a little incomplete. Incidentally, the Earth is not the center of the universe in this system. The Earth is the bottom of the universe. That's where everything falls. It's like the sump of the universe. And after all, what's inside the universe? What's inside the earth? The inferno. That's, hell, basically. If you said that the earth was special for being the center of the universe, that would make hell even more special than the earth. It's the other way around. There is an interesting problem with this picture. You know the size of the earth. We've measured it. It's a pretty big place. We know how much air there is. It goes up as far as we can imagine. And then when you look in the sky, all the region between where the air is up to where the moon is, that must be that region of fire. So how come there's only a thin layer of water? You would expect, if there were equal amounts of the materials, that the water on the earth would be enormous and would completely cover the earth. How do we get around this? Well, very clever people made the very clever mistake of misreading Scripture and reading where it says, God said, let the waters that are under the heaven be gathered together, and the dry land appears. Now, the guy who wrote this did not have Aristotle's picture in mind. Aristotle hadn't written yet. But 100 years or 1,000 years after Aristotle, people were conflating these two different ideas. And they said, I know why there's dry land. You've got all that earth and all that water, but God moved the water off to the side and left a little bit of dry land. Center of the universe is still, or the central point is still where the land is. The water has been moved to the side. Notice in this picture that as you move away from the dry land, the water gets deeper and deeper and deeper and deeper and deeper. Due north is actually more like that. And then when you go sailing on that ocean, you're sailing farther and farther away, so you're actually sailing uphill. And that's why they call it the high seas. Not only that, if you're Christopher Columbus, that's why you know once you leave Spain, you're not ever going to run into dry land until you make it all the way around to the other side of the disk. It's built into the way you look at the universe. Now, that seems pretty absurd. People didn't really believe that. Well, they did. And they had some really good reasons to believe. Because when you go to the ocean and you look at the horizon, and it's a nice clear day, and you've got a tube, you don't even need a telescope, just a tube, and you orient it to the horizon, you notice that you actually have to tilt it up a little bit. Of course, it's kind of weird because it's different from day to day, but basically, more often than not, you're tilting it up because you can see the water is higher than the going straight out. We now know that that's due to the refraction of the air that acts like a lens that makes the water appear higher. They couldn't have known that. They said, oh, if the water was higher, we should be able to see it. We can see it, therefore the water must be higher. Really good science. Wrong, but really good science. What's more, if you've got a lump, what's going to be in the center of that lump? The most important city in the world, Jerusalem. It all fit together beautifully. If you think this is weird, and I'm making it up, this is what my friend Chris Graney came across. A number of pictures depicting the world like this. And we're not talking the Middle Ages. We're talking, in fact, 1663. After Galileo's telescope. And they're still talking about the water being pushed to the side, and that's why we have springs, because it's going through the cracks in the water. As late as 1777, this is being used as proof of the existence of God. Science proves God. If science proves a God, then that God is subservient to science. I'm not sure that's the God I want to believe in, but never mind that. In this catechism, the vast sea of which there's such abundance as would be higher than the earth are nonetheless bounded and restrained by God. Therefore, there must be a God, otherwise we'd all be swimming. Once you have committed yourself to this way of looking, you're going to see the evidence that confirms what it is you already believe. And you're going to be ignoring the evidence to the contrary. As far as the idea that the dry land was, surrounding Jerusalem, well, clearly that's absurd. Except if you actually look at the earth today and include the Americas and find a mapping of where the center of the dry land is, it's actually not all that far from Jerusalem. Sometimes coincidences also get you. There's something else, though, about this Aristotelian view of the universe. Again, really good science gone wrong. You've got all of these planets embedded in transparent spheres. Transparent because you can see other planets behind the planets. You can see the moon moving in front of stars. You can even see the moon moving in front of planets. You get the idea after a while. The farther away they are, the slower they must be moving. And it turns out you're right. The difficulty is when you actually measure where the planet is from night to night, it's not a nice, smooth motion. Each dot is where Mars is at a given moment, about 20 years ago. You look at Mars, it's in one of those dots. You go 10 days later, it's moved a little bit. 10 days later, it's moved a little bit. But then it starts to turn backwards. And it also goes up a little bit. How do you explain that with these transparent spheres? Eudoxus figured it out. He says, there's more than one transparent sphere. The spheres are inside of spheres, inside of spheres. It was really clever. It was able to explain what you could see. The difficult part was that it was really hard to calculate where exactly the stars were going to be. If you wanted to predict the positions of the planet, why would you want to predict the positions of the planets? Well, everybody knows that the planets control our lives. Everybody knows that we get sick in the wintertime every year, right? And what else happens in the wintertime every year? There are stars overhead, the same stars overhead. It must be the influence of those stars that makes us sick. And in fact, what do we call that sickness? Influenza, which is the Italian word for influence. It's still part of, built into the language that we have. There's a better way of calculating, though. About 150 years after Christ, Ptolemy worked out that if you have the sun going around the earth, the moon goes around the earth, Mercury goes around the earth, but in a little circle, Venus in a little circle, and the other planets going in little circles, those little circles can then have moments when the planet appears to go backwards. And if it doesn't exactly match, you just add on another little circle. And if you have enough little circles, you can match the positions of the planets. Kind of complicated, but it's circles, and we can do that arithmetic. And we can, add as many epicycles of circles as we want to have as much precision as we want. When Copernicus came up with his system, this is what you have probably been taught, Copernicus said. This is the picture in the front of the book that was added by the publisher, not Copernicus. There's the sun. There's all the planets going around the sun. But that doesn't give you the actual positions of the planets, because those are still circles. And the planets still are sometimes moving faster and slower. If you actually read Copernicus, this is closer to what he still had those little circles. He still had the little epicycles. Even the sun was making a tiny circular motion around the center of the whole system. Now, having this kind of motion allowed you to see that, the planets go backwards because they're going circular on the Ptolemaic system, or as the planet in the inside, moving faster, overtakes the planet on the outside, it looks like the planet on the outside is going backwards. Either one of them can give you the same result. how do you choose between Ptolemy and Copernicus? You might say, well, Ptolemy is more complicated, but only one step more complicated. What's more, there is a problem, and we'll get into the problem, of having the Earth move. Tycho Brahe, and I start this out to remind you, Tycho Brahe had an interesting system. If you have the Earth standing still relative to the outside stars, you have the sun moving around the Earth, and then all the other planets going around the sun. There is no observation of the planets that can tell the difference between that system and the Copernican system, because they're mathematically identical, just with a shift in origin. The only difference is how the Earth moves relative to the final outer stars. Does the Earth appear to move? Well, we can see if we can measure that. Let's say at one time when the Earth is on one side of the sun, a nearby star is in front of those three stars in the back. 6 months later, that same star is going to be in front of other stars. It's called parallax. You get that idea by looking at me, looking at the wall behind me, and move your head back and forth. And you can see that it looks like my head relative to the back seems to move. Tycho Brahe did not have the telescope, wasn't invented yet, but he had a protractor that was 18 feet long that allowed him to measure the positions of stars to a phenomenal precision. And he did not see any parallax. To give you a sense of actually why he didn't see any parallax, we now know today, of course, that the stars really are out there and the Earth is moving. But how much parallax can you actually see from where the stars are? Well, there's 360 degrees in a circle, right? And every degree, 1/360th of a circle, can be divided into 60 minute parts. Why 360? It divides a lot of numbers. It can be divided by 2 and by 3 and by 4 and by 5 and by 6 and so on. Why 60? It can be divided by 2 and by 3 and by 4. So 1/60th of a degree is a minute. Each minute part of a circle can be divided a second time into seconds, 60 parts, hence the word second to go along with the word minute. If you see a shift of a star compared to the ultimately distant stars of 1 second of arc, 1/60th of 1/60th of 1/360th of the circle, that star would be 1 parsec, parallax second, away from us. That means a parsec is a measure of distance, not time. Thank you, Han Solo. The nearest star to us is 2.5 parsecs away, which means that its parallax is that much, less than half of a parallax second. The nearest star. To be able to see that, you have to have really clever, sharp, precise telescopes, and they didn't have those until the 19th century. So, no one could see parallax. What are the implications? Either, if the star is close enough and we don't see any parallax, then the Earth must not be moving. On the other hand, if the stars are really far away, then that would explain why we don't see it when the Earth moves. But boy, they have to be really far away. They didn't know in the 17th century where the stars were. As I say, we didn't measure that until the 19th century. Except they did know. They had a really clever way of measuring how far away the stars were. And the trick was this. You go to your telescope. Galileo has just invented the telescope. You go to the telescope and you look at a star in the telescope, and what you see is a fuzzy dot. Let's assume, reasonable assumption, let's assume that every star is a sun. Let's assume that the size of the star you're seeing is really the same size as the sun, only that much further away. If you saw the star half the radius of the sun, it would be twice as far away from us as the sun was. If it's 1/2000, which is what Galileo thought, then the stars are 2,000 times farther away from us than the sun, which is still pretty darn close. When you make this assumption, then you conclude that the stars must be close to us. Galileo early on said, well, all I have to do is look at the right place and eventually we'll see this parallax. They never did. The trouble is, that's not actually the star you're looking at. Why? What were they getting wrong, thinking that that fuzzy disk was the star? The trouble is they didn't know, they couldn't have known, it took another 100 years or so, that light coming into your telescope comes in the form of a wave. You guys here live on the lake. You've seen harbor walls. You've seen water come through, waves come through the opening in the harbor wall. And the wave doesn't just cut off when it comes like that. No wave, no, suddenly a wave. That's not what happens. That's what happens. The narrower the slit, the more the water is spread out. And some of the physics majors here may recognize, you may have played with these little, you can actually see in a lab the waves spreading out. Well, that's two dimensions. With a telescope, you've got the light coming through that little hole, and it makes a fuzzy spot. It's called an Airy disk because George Airy worked out the mathematics in the 1830s, which is 200 years after Galileo. So you have to forgive Galileo for not having this worked out. Incidentally, that's Galileo's telescope. Why is it that most of it is covered up? Because a telescope lens, in order to focus, should have the surface of a parabola, and that's really hard to make. Galileo was lucky to make any kind of curve. Yeah, have any of you tried, carving lenses out of glass? Not trivial. What Galileo wound up carving were spherical surfaces, not parabolic, and only at the center are the two so close that you can. So he would make the lens with the spherical surface, block out the parts at the edge that were far away from a parabola, and the image would appear sharper. But what he didn't realize, he's making the image sharper, but he's also making that Airy disk bigger. So he's getting these big fuzzy images for what ought to be a point. Let's take a look at how that works. You've got that disk of light, but of course it's brightest at the center and then dim as it goes farther away. And that width is entirely a function of the geometry of the opening of the telescope. So that's what one telescope would look like, or one star at a telescope would look like. If you're looking at a second star, which is half the brightness, the width is exactly the same because you're using the same telescope. It's only the height that's different. Well, here's the other thing. The human eye cannot see all the way down to perfectly faint light. There's a cutoff. Let's add that cutoff. What you see now is that brighter stars are going to look bigger in the telescope than fainter stars, because the cutoff hits it at a different part of that curve. My prediction was that every star is like the sun. Reasonable first guess. If I see a brighter star, it must be closer to me. If it's closer to me, it's going to look bigger in the telescope. By golly, it looks bigger in the telescope. I must be right. When in fact, they're wrong. They're wrong in so many different ways that they could not have known in the 16th century. Starting with, most stars are not like the sun. Yeah, the sun is a star, but the vast majority of stars in our galaxy are way smaller and fainter than the sun, and some of them are actually a whole lot larger than the sun. Of the 100 stars closer to us in the solar system right now, 80 of them are so faint you can't see them with the naked eye. And of the 20 brightest stars, most of them are at enormous distances. They just happen to be a kind of star that's a heck of a lot brighter than our sun. Let's go back. If the stars are nearby, then you ought to see them, the parallax. We don't see the parallax, therefore the Earth is not moving. If the Earth is actually moving, then the stars must be very, very far away. But if the stars are like our sun and have sizes the way they seem to have in the telescope, they have to be there nearby, and therefore the Earth cannot move. And therefore Copernicus is wrong, and therefore Galileo is wrong, and the only way you rescue that is this kind of goofy system that Tycho Brahe had of the sun going around the Earth, but at least it fits the data. In spite of that, there are still some people who insist Copernicus is right, because they're clever. They have come up with, maybe I can relax one of those assumptions. Maybe stars are not like our sun. Maybe stars are really, really far away, but the size I see in the telescope, because they're enormous. Tycho Brahe, who didn't believe that, worked out the relative sizes of stars and planets, and he's not really all that good, but it's not that bad. The people who insisted that Copernicus was right wound up with stars that were that big compared to the planets. And we say today, clearly absurd. Actually, there are stars that big, we now know, out in the universe, just not many of them. All of the work that went into trying to understand the size of the universe was based on assumptions that were very reasonable, but wrong. And remember that when people talk about the universe today and what we know today. It's still based on assumptions that are very reasonable until we find out they're wrong. And when we find out they're wrong, we don't wail and gnash our teeth and say, oh no, terrible. We rather say, this is cool, because I'm going to learn something new, something I didn't know before. This is not science going wrong, it's actually science going right. Let me give you an example of that. Kepler, as described in this wonderful book by Job Karantaram, who is the guy who taught me philosophy of science. Kepler has the idea that maybe, instead of all those goofy epicycles that Copernicus had, I can get away from that by having stars move around the sun in ellipses. And he works out the numbers, and the numbers work. The interesting thing, of course, is that the idea that stars are in ellipses came to Kepler not because it was mathematically more elegant, but because it was theologically more elegant. He argues that what's the most important thing in the solar system? The sun. Well, that must represent God the Father. And the light coming off the sun is the Holy Spirit. And he comes up with this entire philosophy and theology, which is utter nonsense. But in order to have the sun not moving a little dance out around nothing, because God wouldn't be making a little dance around nothing, he comes up instead with a universe where planets are moving in ellipses, because that allows every planet to have its own ellipse, and the sun is at the focus. What's the difference between this system and the Ptolemaic system? There is this interesting difference. The Ptolemaic system, if you add enough epicycles, will exactly match the motions of the planets. Kepler's system fails when you go to a higher precision, because it doesn't account for the fact that one planet's pulling on another planet. Ptolemy is more accurate, but it is sterile. Kepler's system allows you to work out Newton's law of gravity. And thanks to Newton's law of gravity, we now know that his laws derive the elliptical orbits of planets. By not being 100% correct, Kepler actually pushes science further. There are times in science when you have to take off your glasses and sort of see the general pattern and not get too worried about any individual tree in the forest. So I've gone through a number of examples here of how science in my field of astronomy made some very reasonable assumptions and came up with some, ideas that we now know are ridiculous. That's great. There are times, though, when the ideas that were more than ridiculous also have consequences that maybe aren't quite so amusing as the high seas. And that's where, this is what originally inspired me here. You can find vaccine skeptics anywhere, all populations, all demographic populations. You find it especially among certain religious groups. And in this article in the New York Times, the Anglican priest Trish Warren suggests this is actually coming out of a division in our culture between science and religion. The science versus faith discourse isn't an abstract ideological debate, but a false dichotomy with disastrous real-world consequences, is what she writes. Skepticism of the vaccine can show up as a social or a political motivation. It's a tribal marker. It's, I'm one of these people, not one of those. And so when you say, I'm going to believe in the vaccine because I believe in science, and people say, well, maybe I don't believe in the vaccine. I guess that means I can't believe in science anymore. You wind up with a split that, regardless of which side of the tribe you're on, I don't think you want to make. You make science a tribal marker, and that doesn't make science any good. It doesn't do science any good. And what's more, there are times in biology, in medicine, when they have gotten it wrong. We don't see it much here, but, I live in Europe half the year, and I run into people of my age and older who are victims of thalidomide. It was thought to be a safe aid for morning sickness, but it led to birth defects. The FDA refused to allow it in America, but it was used quite a bit in Europe, especially in England. Vaccines don't have a perfect history. They may be the best thing we've got, but they're not perfect. Their safety is something that takes years to test, and, during COVID, we didn't have years. We took a chance. Mistakes can happen. Mistakes do happen. But there's something even worse than vaccines going wrong or medicines going wrong. And something that I think is at the root of why people see a split between science and religion. And it was the abuse of the theory of evolution that led to the idea of eugenics. This image looks really creepy to us today. But this was classic Sunday supplement pop science of 1900. This was an idea that was pushed by H.G. Wells, was pushed by Alexander Graham Bell, who writes in the National Geographic about how we are going to improve the human race by making sure that unfit people are sterilized and only fit people are allowed to have children. And it's especially nasty in the United States because it was an excuse to keep horrible people with vowels at the end of their name, like my grandfather, from coming to America. Incidentally, it explains why the Irish are so stupid. My mom's Irish. Why? We all know that the Irish are stupid. Everybody knows the Irish are stupid. So the argument goes. Well, I can explain why. All the clever Irish men become priests and don't have kids. It's only the stupid ones who have kids. This is the kind of awful argument that's being made not only in the popular press, it's being made in scientific literature. It's very odd that the idea of, what makes a superior person, strangely enough, a superior person is someone who looks just like me. And obviously I'm superior to the rest of you people. This is tied to the anti-immigration movement in the early 20th century, which is not just a left-wing or a right-wing thing. The right wing didn't want its culture, its Yankee culture, polluted by people who are going to be eating pasta and meatballs. The left wing didn't want all these cheap laborers coming in and ruining the power of the labor unions. So this unholy alliance passed laws in the 1920s that not only limited the number of Italians, fortunately my grandfather was already here, it actually forbade any immigration from Asia. And this law was on the books until the 1970s. And the idea that inferior people, who oddly enough mostly were of minority races, should be sterilized was going on as late as the 1970s. It's not just something that, was in the distant past. Of course, it's all tied in with the idea that science and technology, which is usually confused in people's heads, by golly, that will solve all of our problems. Who needs religion? If we just had a sophisticated, technologically advanced society, then all of our problems would be gone. Yeah. And then you've got 1930s and 1940s Nazi Germany with the most technologically sophisticated death camps. To see how this is tied into the science-religion debate, you can only just look at the book that was used by Scopes in the famous trial. He's teaching evolution and he was put on trial. You can find that book in Google Books today. It's all about eugenics. It's all about breeding superior people. It's all about how my race is superior to everybody else's race. It's a nasty bit of work. And the people who are speaking out against it, the only people speaking out against it, didn't necessarily know that the science was junk science, which it turns out it is. They just knew that it was immoral. It was the churches saying that there was something wrong with this. And if the churches are, supporting the Poles and the Italians, well, obviously those must be the Catholics. And therefore the Catholics must be anti-science because science is going to save the world with eugenics. But underlying this, just as underlying the general distrust of science when vaccines or medicine goes wrong, is a misapprehension of what science is. The vaccines prevent the disease for the overwhelming majority. There are cases where it doesn't work. It's not perfect. The fact that there are failures makes you think, well, there's something wrong with the system. The fact that people say, follow the science, makes it sound as if science is perfect and we can follow it like we were following Jesus. A fear of a blind trust in science has an element of truth behind it. But if you actually study science, the first thing that they really make you study is error. Calculating error, working out where the odds are. We've all heard this phrase, failure is not an option. The guy it's attributed to, Gene Kranz, used that as the title of his book, and in the book he says, I never said that. Because in science, failure is not an option, it's a requirement. I wrote papers, when I was a grad student 50 years ago. Those papers are wrong. And I'm proud of the fact that they've been found to be wrong, because it meant that they were interesting enough that people kept working on it and found the places that were wrong and found the places that needed to be corrected. If nobody ever found anything wrong with my paper, it's because the paper was useless and nobody ever bothered to read it. I'll give you a different example. When I was at MIT, I was on the sailing team. I managed to sail for 3 years and never once capsized and never once won a race. That's what it takes to win a race. To push things to find out where the edge of the envelope is. To push things to find out, all right, that made me capsize, let me dial it back a little bit. That's how we learn. We learn by making mistakes. And learning to fail is difficult, but then we have developed the mathematics to work out the probability of, all right, these many failures are to be expected for this kind of theory. And if I'm getting more than that, then I realize I have to pull back and figure out what else is going on. Learning to fail is hard. You've got this balance of pushing an idea, even though it doesn't quite work. If only I work out a little bit more, it will work, versus saying, it's not working because it's wrong. And there's no calculus that'll tell you which way to go. Edwin Hubble, the guy who measured the galaxies expanding, did not believe in an expanding universe. He was wrong. It was a new idea, and he just couldn't accept it. Ernst Mach said that the universe is not made of particles but fields. Boltzmann resisted those fashionable new ideas, and it turns out in that case, Boltzmann was right. Just because an idea is new doesn't mean it's right, doesn't mean it's wrong. And there's no easy way except being open to the possibility that I might be wrong, but having a hunch and hoping that your hunch might play out. But more than that, getting the right answer isn't actually the point of doing the science. It's just a way of judging how good our current understanding is. There's the Copernican system with all the epicycles, or actually the Ptolemaic system with all the epicycles, and then Kepler's orbits. As I say, Ptolemy can actually give you a more accurate picture of the universe. But if you go to YouTube and you do Homer Simpson Ptolemy, you will find a guy who has worked out a way of tracing the picture of Homer Simpson. So if therefore there was a planet that orbited like Homer Simpson, Ptolemy would be able to work it out. The difference is that that system doesn't tell us what gravity is. Being wrong allows us, being a little bit wrong allows us to see the bigger picture, the bigger principles behind what's going on. This is a radical idea in many ways because of the way that we learn science. I've taught science, I've learned science. When you're taking freshman physics, how many people here have had freshman physics? What's the goal of freshman physics? To get the answers in the back of the book. And it tells you that truth is the answers in the back of the book. Well, guess what? If that were physics, it would be the most boring thing you could do. Actually, physics in freshman year is not physics any more than playing scales is the same thing as playing music. Getting the answers in the back of the book is a finger exercise to get you used to the feel of what physics feels like, so that you can go on and actually do real physics where you don't have a book and you don't know what the answers are going to be. And that's a whole lot more fun. It's also true in faith. That book that I advertised at the beginning, When Science Goes Wrong, it's published by Paulist Press, a religious publication. Because ultimately, this is a lesson we take to our faith. Anne Lamott, in this book, Plan B, has this marvelous phrase, the opposite of faith isn't doubt. The opposite of faith is certainty. If I'm certain, I don't need faith. Famous story. The preacher has his flock. He goes down to the river. He says to the people, do you believe that I can walk on the water? Do you believe? And they, we believe. Do you really believe? Yes. Do you honestly, in your heart of hearts, know that I can, if you have the faith, then I can walk it? We believe. We believe. Well, if you believe, I don't have to do it. And actually, what she's doing is quoting Paul Tillich on the dynamics of doubt and faith. This is what science looks like. It's not perfect curves. It's a scattering of points because there are a lot of things that can distract from the general pattern. You don't ask for perfection. That desire for perfection is what misleads a lot of people who don't know science. You're saying that, scientists have to be skeptical, question authority. Somebody had a button like that and I said, question authority, says who? What eventually happens is that we have this demand for perfection in our truth and a distrust of authority, the only thing that might actually get us closer to the truth, and our brains squirt off in a third direction so that we decide the authorities don't know, but the truth is out there, and I can find it on the internet. The idea that you're going to find the truth on the internet is as old as the snake saying, oh, I can tell you the truth that God doesn't want you to know. As a result, a lot of clever people wind up not believing what, orthodox science is trying to say, knowing that we're wrong and that being wrong is how we progress. And they then say instead, oh, nobody believes in UFOs. I'm going to believe in UFOs. Why? Because I'm smarter than everybody else. If I'm the smartest guy in the room, how can I agree with everybody else in the room? What's the point of being smarter than them? So if nobody believes in UFOs, I'll believe in UFOs. If everybody believes in vaccines, then I'm going to be different. It's that kind of arrogance that you find in a lot of engineers who are really good at making widgets that work, but are used to thinking, well, all the suits don't know what the hell is going on. I can do that better than... They couldn't do anything without me. Of course, you couldn't do anything without the suits, but they don't want to admit that. It's the arrogance of, say, a really good athlete who thinks he's smarter than everyone else. Though you wouldn't know any about that in Green Bay. There's one last point, though, that I want to make in all of this. If you're doing the science just to make a buck or to make things better or to prove that you're smarter than the other guy, at the end of the day, you're going to be frustrated. You're going to feel empty. Why do we do the science? It's not to show up that I'm smarter than other people. The actual science isn't even to make vaccines or to make, widgets or iPhones, though those are wonderful things. We do the science at the end of the day out of love. We do the science because we see a universe and we can look at it and say, this is good. And I love doing this. I love my science. I love doing the science. I don't like being wrong, but I also realize that being wrong is the way that I can come to be a little more right. Love doesn't demand perfection. Love admits of error, of doubt, of mistakes, both on our parts and on the parts of the people we love. If you demand perfection of others, you can never admit the imperfections in yourself. And if you don't admit imperfections in the world of science, then you'll never learn anything new. But in the general world, in the world of faith, in the world of love, you will never grow. That's the nature of love. That's central to God's love to us. I think again to the fellow I talked about at the beginning, the father who, didn't believe in the vaccine. And among his last words to his daughters were, apologies. He was wrong. Sadness. His daughters love him. Because the fact that we make mistakes is not a reason to stop loving. Thank you very much. So, Times for questions?
Yes, if anybody has any questions, I can run a microphone to you.
I am a scientist.
Mm-hmm.
I believe in science.
Yep.
Okay. You mentioned Hubble. There was a Jesuit who corrected him, Father Lemaitre.
Lemaitre,
And
I hate to admit it, Lemaitre was not a Jesuit.
oh, he wasn't.
No, it is possible to be smart and not be a Jesuit.
Well, he had a problem with some who did not believe that there was a big noise.
Yep,
This was the name that Lemaitre gave to this.
right.
And that person called it the Big Bang. Can you talk about the
Right.
people who were wrong in this instance?
Oh, the whole story of the Big Bang is fascinating. Once the universe seems to be expanding and matches what Hubble predicted for the Big Bang, there was a fellow in particular, Fred Hoyle, who was, a good English scientist, which is to say he was an atheist. All the scientists that you hear of as atheists tend to be British, but that's a whole different issue. And he came up with an alternate theory that could explain everything that we saw in the Big Bang without there being a Big Bang. And it was a really good theory because it could be tested. Meanwhile, Lemaitre had come up with this idea of an expanding universe and that you could run the film backwards and figure out when the universe was made. And Pope Pius XII, speaking to the Pontifical Academy of Sciences, says, "Isn't that interesting? The scientists are telling us that the universe had a beginning. Ha! We could have told them that." Lemaitre is now being, jostled on both sides. Lemaitre actually went to Pius XII and said, "Don't say that. Number one, maybe I'm wrong. Number two, whatever I'm saying is going to look ridiculous in 1,000 years' time, so don't base Catholic theology on something that will be 1,000 years old and out of date." But more to the point, the creation from nothing is not the same thing as the Big Bang. The Big Bang happens in a universe where there are laws of physics and space and time. And what God creates are the laws of physics and the space and the time. On the other hand, Fred Hoyle has this alternate theory. They actually had a big meeting at the Pontifical Academy of Sciences in the 1950s where Hoyle and Lemaitre finally got to meet, and they became best friends, because they're both interested in the same thing, and they are both more interested in finding out what is actually true than scoring points off the other guy. Eventually, Hoyle's theory was testable, and it failed the tests. And that's why at the moment we use the Big Bang. It's the one we've got that matches all the data. But as we've seen before, just because it matches all the data doesn't mean it's true. And, the James Webb is seeing things that make us realize, oh, it doesn't quite work. Does that mean we throw the theory away? Or does that mean that we tweak the theory that we've got? It could be either. That's why it's so much fun.
Yeah, Brother Guy, what are your thoughts about you and your fellow astronomers thinking about extraterrestrial life?
It certainly seems reasonable that there could be, but we haven't found it yet. And part of the trouble with it seems reasonable is that we're human beings and we still expect to see. You see the sun, you see stars, and your first guess, reasonable guess as well, the stars are suns. Turns out they're not. You see, we have planets here, we discover planets around other star systems, and your first thought is, well, they must work like ours. Turns out they don't. Our imagination isn't nearly as broad as what the universe can hand us. On the other hand, it's still a huge universe. The farther away you look in space or time, the greater the odds are that there would be something there that was intelligent. But the farther away you look in space and time, the lower the odds are that you'll ever find it. And that's kind of, where we're stuck at the moment. Ask me again in 1,000 years.
Something that I've been wondering about this topic before is what would your advice be for how we continue this dialogue going forward with the people here at SNC when we no longer have such an incredible expert here to guide us?
Part of it, I think, is to take advantage of what you've got at this college, at this university, which a lot of places don't have. You've got first-rate theology and philosophy along with physics. One of the problems of the so-called new atheists is that they tend to be these ancient British white guys. No, I've got nothing against old white guys, but still. In Britain, they're not allowed to study philosophy, and so they think they can make it up. When I was a Jesuit, they forced me to study philosophy, and I discovered that, number one, it's not just BS. There actually is content to it. And number two, it's actually really hard to do right. And the guys who do it right are pretty amazing people. To be able to reflect on what it is we do, to have the guys who are taking physics take a philosophy of science class, to have the philosophers actually find out what quantum theory is rather than what some Sunday supplement says. That's the kind of dialogue that you can do here better than most schools because you've got the expertise here. And it could be a really exciting thing to do. For all I know, you're already doing it. I'd be surprised if you weren't.
I think this is a line from Francis Thompson. He said, when you touch a daffodil, you disturb a star in the universe. And then secondly, I think it was Sigmund Freud who said, whenever I had a great idea, a great insight, darn it, a poet was always there first.
Yep. It is poetry. Science is poetry. I already did this once and I've already forgotten which is it simile or metaphor when you use the word like? Simile. So, the path of a falling rock is like the solution to this equation. The equation is poetry. And what does poetry do? It takes one picture and eliminates the other things so I can look at that one thing. What does poetry do? It gives me truths that remain true even when my cosmology changes. What Scripture tells me about God, that God is outside of nature, that God creates deliberately and logically and beautifully, all of that's true, whether I believe the cosmology of the Babylonians or the cosmology of this year or the cosmology of 1,000 years from now. And that's expressed in poetry. But like all poetry, you got to live with it for a while. You've got to look around and see other things, and then you go back and you say, oh, I never knew that was there. So astronomy is poetry.
If there is intelligent life elsewhere, how does that fit in with the Catholic faith?
Well, the idea that somehow we're unique as human beings is not traditional Catholic belief, and certainly not traditional Judeo belief. It comes out of the humanist movement, the Enlightenment. The Enlightenment was sort of the adolescence of human thought where everybody came up with great ideas that sounded cool and turned out to be wrong. In our tradition, we already have angels, which are creations that are not human beings, but in a relationship with God. Well, you can say that they're symbolic, you can say that they're mythology, you can say that they're literally true. It doesn't matter for this argument. We're willing to accept that God made creatures other than human beings that are in a relationship. You can find many places in the Psalms, in the prophet Baruch, where God calls the stars by name and they shout to him with joy. Now, I don't think stars shout the way I do. It's poetry. Doesn't mean it's not true. Means, in fact, it's very true. Now, I think there are some things you can say. I don't think there's a fourth and fifth and sixth and seventh member of the Holy Trinity, one for each part of creation. It's the same second person of the Trinity. But what else do we know about the second person? We say Jesus Christ is the second person, but we also say he's the Word. In the beginning was the Word. And the Word was with God, and the Word was God. And archeato logos. I took Greek in high school. Logos. The root of that word is the root of the word logic. God created, not only created logic, God is logic. I wrote this goofy book, and it's deliberately goofy, with my buddy Paul Muller. Would you baptize an extraterrestrial? And it goes into a lot of other questions besides that. It's, kind of we were going to call it all the stupid questions people keep asking us. But in fact, they're not stupid. They're just questions that don't have answers. They don't have answers in the back of the book kind of answers. But they make you wonder, well, should I baptize an extraterrestrial? Makes me wonder, what actually is baptism? What does it do? What is its function? How does it look, in a science fiction setting? And I don't have the answers to that, but I think it's a fun thing to think about. And maybe write a fun science fiction story about.
This goes off from your book, Would You Baptize an Extraterrestrial? Would you try to convert an alien?
If you read the book, you'd know my answer. Available at Amazon.com. Such a good book, you should buy 2 copies. But since you came here, I'll give you the answer I give in the book. Would I baptize an extraterrestrial? Only if she asks.
Well, let's all thank Brother Guy. As our evening concludes tonight, I just have a few closing remarks. Outside, a desert reception is available, and all are welcome to spend some time enjoying some of the hospitality before you leave. And of course, while the young Jesuit order has many esteemed scientists, did you know that the more ancient order, the Norbertines, also has a lot of great scientists? Outside, you will see a lot of banners prepared by Dr. Michael Holstead, the director of the Center for Norbertine Studies. Please check them out. The Norbertines have done great things for science as well, and there are beautiful banners outside to demonstrate some of that work. Our campus bookstore has acquired copies of several of Brother Guy's books, and they are available for purchase just outside of the theater. They will also be available in the campus bookstore for the next couple of weeks, so please check out some of those books if you're interested in tonight's talk. And also making our way around the natural sciences. Next year for this esteemed lecture, we are going to be looking at biology. As details evolve on that, wink, wink, we will be sure to share them with you. So next year we're hoping to talk about evolution and the faith. A big thanks to Julie for helping out with this great project, and thank you all for being here. Have a great night. Let's thank again Brother Guy Consolmagno.